and welcome back to Heroic Physics for our special 5th episode. At Heroic Physics, we use superheroes and the occasional science fiction reference to help you understand physics. And today's episode, we will be measuring the acceleration due to gravity.
Billions of years ago, a universe was born. A universe governed by the laws of physics and held together by 4 fundamental forces, the weakest of which is gravity. Gravity, while weak, increases with mass. This weak force comes to govern very massive bodies, forming planets, satellites, and stars from dust. Moons are placed in orbit around planets. Planets in orbits around suns, centripetally pulled by the force of gravity. And all living bodies' first experience of this physical force is due to the measurable acceleration of gravity when apples fall.
And what's special about today's episode? Well, in the past, we've only done conceptual physics. And today's episode, we will be doing experimental physics. And who better to help us than a special guest star of Green Lantern?
How's it been?
Good. Wow. From good. We're not in costume.
Yeah, well, Hispanics isn't for everyone.
So they look better on you than some other heroes I know.
That's true. The Flash can't pull off spandex.
Yeah, he can't. Are you ready to help us measure the acceleration due to gravity today?
Of course, from my time in space, I've had a lot of experience with gravity.
That's exactly why I asked you here today, Green Lantern.
You could drop the green.
So just Mr. Lantern?
Lantern would be fine.
To review, what is the force of gravity?
Force of gravity is the attraction between 2 objects with mass.
Since gravity is a force, what does it result in?
Well, acceleration, of course.
Where does the force of gravity pull?
It pulls towards the center of the object with mass. So in our case, humans would be attracted to the Earth's core.
Exactly. That's why exponentials fall. And why I can't jump to space. Now, how does the force of gravity compare at more massive planets?
That would result to a stronger force of gravity and also a greater acceleration.
Exactly. I wish all my guest stars were as knowledgeable as you, Lantern.
No need for flattery. I'm just doing my part to help the younger people understand physics. Besides, I know I'm great.
You're too modest.
What can I say? Physics is great.
How about we go measure the acceleration due to gravity?
Sounds good. Hold on to me.
Wait, what?
I'm gonna fly us there.
Oh, okay. Your arm's very muscular.
I know. Hold tight.
Oh, wow. Just, wow.
You can let go now.
Okay, but still, wow. I've never flown before.
You wanna see the Flash doing that?
We're going to be using 3 everyday objects to measure the acceleration due to gravity here on Earth. First, we are going to use this tennis ball. Secondly, we're going to be using a tape measure. And lastly, we'll be using the stopwatch app on a smartphone. What we're going to be doing is this. Lantern here is going to be dropping this ball from an elevated ledge from west. Lantern, if you're dropping this ball from west, what is the initial velocity of the ball?
Well, that would be 0 meters per second.
Correct. When you're dropping something, it does not start with a velocity, but once you let go, the force of gravity is now acting on the ball unopposed. And because of this, the ball is going to be falling with the acceleration due to gravity. We know the ball will be falling with a constant acceleration due to gravity. For example, if I'm accelerating at 5 meters per second square, that means I'm adding 5 meters per second to my velocity every second. In 1 second, I will have gained 5 meters per second to my velocity. In 2 seconds, I would have gained 10 meters per second to my velocity. To calculate the change in velocity of an object while it's accelerating, we will take the time it's accelerating for and multiply it by the acceleration it is accelerating at. When we multiply acceleration by time, we will either get the gain of velocity over that time or the loss of velocity over that time. If we want to find the final velocity, we would take that expression for the change of velocity, being acceleration times time, and add it to the initial velocity to get the final velocity after it's done accelerating. Disclaimer, for this episode, we will be considering downward velocity and downward acceleration as being positive. What else can we conclude about the ball's motion?
Well, since the acceleration is constant, we can conclude from that the ball spends an equal amount of time at each velocity.
Because of this, we can calculate the average velocity using the initial velocity and the final velocity. This average velocity being the equivalent velocity of the ball going the same displacement in the same time. Average velocity is just equal to the initial velocity plus the final velocity divided by 2. When we drop this ball, we will not know the velocity of the ball before it hits the ground. We will, however, know the initial velocity, which is
0 meters per second.
To calculate the final velocity, we're going to take 2 measurements. The time it takes the ball to hit the ground and the height the ball is released from.
And if you guys want to be cool at home, try this yourself. Or at least do the calculations.
Thanks, Lanton.
That's what I'm here for.
No, I feel like you tell all of the physics percentile staff.
Alright, well, first of all, you're the only physics presenter I know. And second of all, I'm a superhero. Alright, I can't be letting down the public to have a little sandwich. Have you seen how long it takes for the Flash to eat a sandwich?
I have not.
It is one of the slowest things imaginable.
Really?
He always delicately unwraps his first sandwich.
Wait. Full sandwich? Just how many sandwiches are we talking about here?
About 15 on a light day.
Wait.
25 most days.
I thought he said he was on a diet.
Oh yeah, what a diet. He stopped putting bacon on everything. He stopped eating meatballs.
I'm not sure that counts as a diet.
Yeah, I remember this one time I came in and I yelled, Flash, the weather wizard, the trickster, Heatwave, Captain Boomerang, Captain Cold, they've all escaped Iron Heights. And he said he'll be there in a flash, after he finishes his first sandwich. And after me and the Justice League come back after catching him, he's still in there on his third sandwich.
He really has a slow metabolism.
Yeah, well, not all superheroes have fast ones.
Yes, that's for sure. Here, catch.
Alright, I'll go up.
Thanks, Lanton.
No problem.
Lanton is now going to be releasing the ball from this edge up there from the same height each time. So now we're going to need to measure how high up Green Lantern is going to be releasing the ball from. Using this tape measure that has units marked out in centimeters. How many centimeters is this, Lanton?
167 centimeters.
Now, we're going to want this distance in meters. 1 meter, by definition, is equal to 100 centimeters. If we want to go from centimeters to meters, we would take the amount of centimeters we have and divide it by 100 centimeters per meter. So we take 167 centimeters, divide by 100 centimeters in a meter, and we get 1.67 meters. I'm going to measure with my stopwatch how long it takes each time and write it down. We're going to do this 5 times for 5 sets of data. We're then going to average all of these calculations together to get an average calculation for the acceleration due to gravity as go. 0.55 seconds. Go. 0.56 and go. 0.49. 0.55. Go. 0.8 seconds. We have our data. So we're going to go off to a whiteboard to calculate the acceleration due to gravity with our data.
Want to grab it on?
So, okay. So here's our data table. We have time, initial velocity, and distance the ball went. The initial velocity will be the same each time since we're dropping it, which means the initial velocity was
0 meters per second.
We also knew the distance would be constant because we were going to drop it from the same height each time. And we measured this height to be
1.67 meters.
And now we're going to fill in the times we measured. 0.55 seconds, 0.56 seconds, 0.49 seconds, 0.55 seconds, and 0.80 seconds. Now with this data, we're going to calculate the averages, and then we're going to calculate the average answer using our average data. Sound cool? How do we find that average?
Take all of your data points and divide by
The total amount
total number
of
of data points.
What is the average initial velocity for 5 initial velocities? That's 0 meters per second.
I'm still calculating. 0 meters per second.
Now our average distance will be,
1.67 meters.
and now our time measurement. We take 0.55 seconds plus 0.56 seconds plus 0.49 seconds plus another 0.55 seconds and then plus this 0.8 seconds, and we get lantern
0.59
0.
seconds.
Now we are going to calculate the acceleration due to gravity using these equations. Average velocity will be equal to the average distance covered over the average time. And also we know our average velocity has to be equal to what?
That would be our final velocity plus our initial over 2.
We also know that the final velocity after you've been accelerating is final velocity equals your initial velocity plus the velocity you gain or lose. Your acceleration multiplied by how long you've been accelerating. We're going to take the average distance and the average time and put it into the average velocity equation. And we get the average velocity will be the distance, which was always the same, divided by the average time it took to get that distance. We're going to take the average velocity from there, plug into the other average velocity equation, and solve for our final velocity, our average final velocity for this time. Then we'll take that velocity final, which is our average velocity final because we've been using the average of all of our measurements so far, and put into the velocity final equation. We know the initial velocity is 0, and we're going to use the average time to calculate the average acceleration due to gravity. Calculator.
2.83 meters per second.
Equals.
5.66 meters per second.
Equals.
9.59 meters per second squared.
I would like to thank Green Lantern for doing the calculation part on the calculator.
And if you guys were cool, you would have done this along at home.
What we have in reality, if you were to be in your physics class and look up the acceleration due to gravity here on Earth, the accepted value is 9.81 meters per second squared. And now, since this is a special acceleration due to gravity and not just an acceleration, we use a different letter to represent it than just the letter A. We use the letter G.
For Green Lantern.
No, but if that helps you remember it, go right ahead. We are almost done. You're probably wondering, how close was our measurement? How much did we mess up? Well, in physics, there's an equation for that. It's your relative error equation. Green Lantern, do you know what the relative error equation is?
I do not. What is it?
The relative error equation, which can also be called the percent error equation, is equal to the measured value, what we measured in our experiment, minus what the value should have been, the accepted value, all divided by the accepted value, what it should have been. The top part just tells us how far away we were from the value we wanted. And the bottom part, where we divide by what it should have been, the accepted value, it will tell us the amount of it we were off by. To get the percentage, we now multiply by 100%. Our error in our measurement was, and our percent error, Lantern, was
2.24%.
and that is relatively good. In fact, you will hope to have less than 5% error. Because our error was only 2.24%, we will accept our value as being a good measurement for the acceleration due to gravity here on Earth.
Now don't be fooled. This 9.81 meters per second squared isn't the acceleration of gravity for everywhere. That's just for here on Earth. I would know. I've been to other planets.
Depending on the planet's mass, radius, and density, every planet has its own unique acceleration due to gravity. Here, it is 9.81 meters per second squared, but don't use it on the test when you're calculating things falling on the moon or on Jupiter. It's a common mistake to make.
Yeah, well, I'll be busy saving the galaxy to come anytime soon, but if you ever need me to explain physics again, I'll be happy to help. Well, see you guys at home. Stay green.
Now come back next time for an episode on free fall and terminal velocity with a new guest star who's not quite as dark of a night as we've had before here on Heroic Physics. If you Untitled Chapter has less mass in this radius,